Hello class, I'd like to start off by thanking you for joining me today. I'd like to tell you a little story about my little brother Ramsey. When he was about 3 years old, he'd always say that he'd be scared of the dark. He said that he'd want his door open and the hallway light on, and I thought that instead of doing all that, I could just buy him a nightlight. And that's exactly what I did. I bought this nightlight. One day, as I was going past his room, I noticed that this light wasn't working anymore, even though it was plugged into the wall. I did a little bit of research and I found that this nightlight had a bunch of resistors, wires, and a light sensor in it. And so with this simple device, my little brother can now go to sleep well at night. And I can also thank Leonhard Euler for his mathematical contribution to circuits. Throughout his mathematical career, Leonhard Euler has discovered multiple important formulas. In an article by Hong titled Euler Identity, Hong elaborates on one of these formulas nicknamed the most beautiful equation in math, I to the power of x plus 1 equals 0. Even though this formula may be one of his more important discoveries, Euler discovered an interesting method in which you can approximate the solution to a differential equation. This method may be difficult to understand, but I'll be breaking it down so you can understand what a differential equation is, how the method works, and how this simple method laid down the basis for more complex circuits. A differential equation is very useful when it's used in the real world. The power of a differential equation lies when research is being done and data is trying to be analyzed. In a 2015 Britannica article titled Differential Equations, a differential equation was described as what can be directly observed and measured for systems undergoing changes in their rates of change. What is basically trying to be said here is that when you're observing a system that is going through a change, you're specifically looking at the rate of change. For example, when you're looking at a wire and electricity is flowing through it, which is the system, you're looking at how fast the rate of change, how fast the electricity is flowing through it. So unlike a normal solution to an algebraic equation, a differential equation has the solution to a differential equation is a function. This is because the behavior of a differential equation can be described as many different solutions that are similar in their rates of change, as you can see in the graph to the left. There are multiple solutions that have the same rate of change, but to find the exact solution, you'll need an initial condition. This is how you pinpoint the exact solution that you want on the graph. For example, if you give this point, you would get that solution. This point that is given is called an initial condition, and the graph that is being found is called the particular solution. Euler realized that there's not always an analytical method to find a solution to a differential equation. Here, Euler had to become creative and create a method to find the particular solution to a differential equation. Euler first used the standard equation of the slope line. This would be the y1 equals y1 minus y0 equals m times x1 minus x0. After rearranging it, he ended up with the slope formula with the slope equaling a set of coordinates. Now, to first understand his logic, you should know that a line such as this is created of infinitely many points. By connecting these points, you can create a line which has a slope. For example, if you analyzed one point, such as xo, this point has a specific slope in which you can create a tangent line. Now, by adding the step h, you can get a new point x1, and if you follow the tangent line, it will give you the new y1 value. And now you can keep this point as a new data point and call it x1 and y1. Now, if you do this multiple times by adding more steps and more steps, you can get an approximation of what the solution of a differential equation is. As you can see in figure 15.34, this solution has been done multiple times, and you are given you're almost given the same function as you have right here. This method of getting multiple data points is called numerical analysis. Now, even though Euler created this formula in 1748, there was no real use of his method until 1830. In Michel Farnham's article of History of Transformers and Inductors, Farnham talked about when the property of an inductor was discovered in 1830 by Joseph Henry, technology was revolutionized because an inductor has the ability to store and release energy. A new aspect was introduced into the circuit. Euler's method became useful here as scientists were now able to analyze a new circuit. Without Euler's mathematical contribution, scientists would have a difficult time analyzing circuits now. Euler's method was created without even the new technology even being available, and now through the use of his method, his technology was able to progress more fast even after his death. Now every time you check your phone, I hope you thank Euler for his work that was done. Thank you.